the invite, Burak. My name is Bharat, and I'm a researcher with background in ion sources and electrical propulsion. I finished my PhD from Homi Bhabha National Institute at Institute for Plasma Research in India, which is the only plasma research institute in India. And my PhD was on development of multi-cusp ion sources, where I designed and developed multi-cusp ring-cusp ion source for electric propulsion application. And all the work that needs to be done in designing an ion source, starting from its analytical studies to 3D modeling, 3D CAD design, manufacturing, everything was done during my PhD. And after my PhD, I started my research associated work at University of Liverpool from April 2023 to April 2026, which ended recently, where I worked with an experiment at CERN in collaboration with AGIS, which is the antimatter experiment, where I worked on low energy antiproton beams for producing antihydrogen atoms. And this is my general background. And currently, I'm in between my jobs, so I'm trying to switch jobs. But since I have a lot of time, so I've been more interested in developing, software codes, which is like my hobby. But I am also very interested and motivated because there were some issues which I faced during my PhD, and I want to come up with some solution. And now I have the time, so why not now? So that's my general background.
All right, sounds great. I could have lots of questions, but I know this session is not for me, so go ahead with your lecture first.
But I cannot share the screen.
Let me help you. Let me help you with that. I need to make you presenter.
Okay.
All right, you're a presenter now, so you should be able to share your screen.
Yeah.
Go on.
Let's see the screen. Okay. Can you see the presentation, I guess? No?
Yes, we can see now.
Okay.
All right.
Let's see. Okay. So
yes, it's full screen now, so it's good to go.
Great. So today's presentation or lecture is going to be on ion optics modeling, in which I would cover some basic things related to designing ion optics and simulation tool which I'm trying to develop called PY-BEMCS, which stands for Python Beam Extraction and Monte Carlo Simulator. And I will discuss what were the motivation about this project that I came up with and how it got motivated during my PhD and so on and so forth. So to start things, here's a general outline of my presentation. So I would start with ion sources because ion optics are part of ion sources. So in general, I would introduce different kinds of ion sources. Since it is more focused on electric propulsion studies, so I would focus on issues related to electric propulsion and how the ion optics are designed for specifically electric propulsion application. Then I would go on to discuss some characteristics of 2-grid ion optics and some tools which can be used to design such kind of systems. And then I would introduce to the two tools that I'm working to develop. One is PY-BEMCS, which is just Python-based code for PIC code for designing ion optics, and the other one is IBSIMU-based GUI. So the backend in this is a very well-known code called IBSIMU, which is used for designing ion sources and beamlines. But I made a Python-based GUI so that it's easier for anyone who does not want to use C++ as a language. So you can directly go on doing more of the engineering things rather than being focused on learning how to code. And at last, I would try to show you some features and demo related to both of these codes. So ion sources, as the name suggests, these are the devices which are used for producing ions in different applications. And what are the different applications? So one of them is particle accelerators, in which you have ion sources. For example, at CERN, you have hydrogen ion sources, which accelerates particle to GeV electrons, and then you have collisions, and then you try to study what are the things inside the most fundamental particles of our universes. Then you have electric propulsion application, in which you have the ion beam coming out of a big, large volume ion source, which propels the spacecraft into the space and produces thrust. And it is mainly used because it is more efficient compared to your chemical propulsion study. The other application is, of course, in semiconductor related studies, in which you etch the surface of different substances like silicon wafers to produce very fine nanostructured patterns for designing transistors and all the other electronic components. So each of these ion sources have different characteristics, very different from each other, which defines them. For example, in deep space exploration, there are ion sources which are up to 5 kV, and ion beam currents range up to 3 ampere, or maybe more or less around 3 amperes. Whereas in surface modification, you have few kVs, but the current is also very limited because you don't want to damage the silicon wafer surface, so you don't need a lot of heating in the substrate. In neutral beam heating, which is used for heating the tokamak plasma in fusion application, you need very high power for heating, so you need very high current and maybe medium energy of ion source. So these are typically neutron or hydrogen-based ion sources. And in particle accelerators, you need very high energies to smash small particle like protons. And in that case, you have energies ranging from GeV to TeV, in which it is accelerated in substeps over multiple cycles. And the current in these cases also ranging from pico to milliampere range. So based on just the magnetic field configuration, there are different kinds of ion sources. Kaufman configuration, in which you have this diverging electric field, magnetic field. You have the line cusp configuration, in which you have this alternating polarity, which provides you a very uniform plasma near the grid. And at last, the ring cusp configuration, which has turned out to be the most efficient, discharge efficient ion source configuration for electric propulsion application. There are other kinds of differentiation in ion sources based on how the ions or the plasma is produced, like RF or electrothrusters, but these are not which I'm going to be focusing on right now. And there are different challenges. So now it comes to the different kinds of challenges. So one of the biggest challenges is to design the ion thruster grids, and manufacturing these grids and studying their lifetime is one of the biggest challenges, which I will discuss in this lecture as well. The other issue is beam transport, how the beam is transported once it is extracted out of the ion source, what are the divergence or the beam profiles of the ion source, and what are the beam diagnostic needed to measure these properties. And the other important area that I think is very necessary is to study how the charge exchange and the beam neutralization process takes place. So ion beam neutralization using electron injections, and then there is also the effect of charge exchange ion, which produces a lot of sputtering on the acceleration grids, and how it affects the lifetime of the grids and the ion source in general. So just to go back in history, the first recorded ion source which made into space was the Kaufman ion source, and in that source, I think the basic design was it was made up of these tungsten wires, which are just looking like they don't even look like grids. So he used these meshed wires, which are woven, just to extract the ions, and it worked to a certain extent. But the problem with these was it eroded incredibly fast, and it also bent under the thermal effects, which ruined the focal length and the divergence of the beam. So, I mean, in practical terms, it worked, but then it had these issues which affected its lifetime. Uh, then after this, people started using multi-aperture grids. So they use these plates, which they use to drill holes or use electrochemical etching to make these multi-aperture grids. But then during the wear test conducted by NASA, they inspected the grids before and after the test, and they found that there were these erosion pattern, which you can see called the pits and grooves after the erosion test. And after a lot of studies, they found that these are mainly caused by the charge exchange process, which happens very close to the grid. Because when the ions are extracted, the neutrals which are present inside the ion source, they are also being leaked through the aperture of the grids, and this creates a very high neutral density region between the grids, and this causes a lot of charge exchange reaction, causing the formation of charge exchange ions. So this is one of the biggest issues with electric propulsion application. The other issue was the thermal deformation. So if you have flat surface grids tied to all the sides, and if you heat it thermally, it will buckle under thermal stress. And to overcome this, what engineers came up with to have large grids, they intentionally bend the grids into a dome shape using thermal deformation processes. And under high thermal loads, these um grids and the extraction optics bent in the same direction and uniformly, so that there was no issue with the shorting of the grids. Now I come to the main application, the electric propulsion and the ring cusp ion source. So this is just a schematic of the ion source which I had during my PhD. So here is the ion source, and here is the schematic. You have the main plasma chamber, you have the heating power supplies for the filament and the discharge which produces the filament. And the most important components which I considered was for me was the ion optics, the screen and the acceleration grid. And on the downstream side, you have all the other diagnostics, which measure the flow of charge exchange ions, which is a radial Faraday cup on the side, and the Faraday cup array, which was used to measure the beam profile. So in this presentation, I would be more focusing on the acceleration and the screen grid design. So to come up with the two grid ion optics, the most important characteristics that defines how much ions or how much charge that you can extract from a gap of two metallic plates is defined by space charge limit, or the Richardson-Dushman Child-Langmuir law. And this is defined by a term called perviance. So perviance is defined by this term on the right, where P is defined by pi epsilon by 9 multiplied by this quantity, where D is your extraction area and small d is the gap between the grids. And, and the current which is extracted out of these apertures is defined by this relationship, which is not directly proportional to the voltage, because if you, it is very analogous to resistance in a normal conducting wire. So if you compare this relation with normal conducting wire and Ohm's law, which is I is equal to VR. So instead of R you have P, and instead of V you have V raised to 3 by 2, because it's a vacuum, and instead of conducting in a normal wire you have this 3 raised 3 by 2 relationship. And so these are the schematic of a two grid ion optic system, where first grid is your screen grid and the second grid is your acceleration grid, and the gap between two is defined by the cold gap. Of course, there is an effective gap which bends under thermal stresses, but I'm not considering them right now for this moment. And the thickness of both the grids is TS and TA. And the way the perviance characteristic work is when you have very large plasma density for a fixed extraction voltage, your plasma meniscus will bulge. And what would happen is it would intercept your acceleration grid, which would cause more erosion, and this would lead to reduction in lifetime of your ion optics. But as you change your plasma density or your acceleration voltage, or the total voltage between the grids, there would be a limit in which all the ion trajectories would form perfectly through this hole, and there will be no interception with the acceleration grid. But if you keep on increasing your acceleration voltage, or if you keep on decreasing your plasma density, there would be an underperviance, which would again cause overfocusing of the grids, which would again increase your divergence, which would lead to the C part of this below curve. And if you still keep on increasing again, your acceleration voltage, then it would cause the focusing of the ion optics just before the acceleration grid, and again the interception at the acceleration grid would start. So this typical scan, you can either increase your current or you can increase your acceleration voltage. Both should give you a typical U-type divergence versus perviance curve. So now I would like to introduce PY-BEMCS, why I worked with PY-BEMCS. So most of the ion optics that are being designed use open source, commercial codes like Opera 3D, which I use in my PhD, COMSOL, which is also a very popular software for electromagnetic simulation, and CST Studio, which again I also use in my CM in my PhD. There are also some free softwares available like IBSIMU. There is Vortex as well, which is a full pick code. But the learning curve for these codes is quite high. So if you don't know C++ or any other like Fortran, it becomes a bit challenging, and you spend a lot of time in learning this code. I mean, you should always try to understand what each code looks like, but let's say if you just want to focus on designing something, I think there should be some tool which just focuses on optimizing and designing the code. And that was one of my motivation. First, that the open source alternative, which can be used for non-commercial research and teaching, that was one of the motivation that I designed PyBEMS. And the another motivation is to use it in Python, because Python is a very, I would say, easy language compared to all the other language. Anybody can learn it quickly and using minimal dependency so that anybody can use it. And it is still under a lot of development. So if you are interested, you can just fork it on GitHub, benchmark it using different tests, and extend it to use it in your work as well. And in the current lecture, I would also like to introduce an extended tool for IBSIMU, which I'm trying to develop, which I will showcase in coming slides. So the main challenges of a beam extraction code is first, the plasma is produced upstream on the left side of your screen grid, and you need two or more grids depending on what your application has to extract and accelerate positive ions to produce the thrust. And the key physics that it should resolve is the space-time limited flow, plasma sheet formation on the screen grid, beam focusing, if needed, the backstreaming effect, which causes damage to the ion source, charge exchange collision in the plume, and if possible, grid erosion, which limits the life cycle of the substance. I think grid erosion was one of the main challenges that I faced that I could not resolve. I did some analytical calculation for my thesis, but I was looking for a code which I could not find during my PhD, which could do grid erosion, which was an open source code available. So just to introduce how the code looks like, in general, there is a mesh, which is a 2D Cartesian grid, and it is the X and Y coordinates, and this is how it looks like, the domain. So the black thing that you see are the screen grid and the acceleration grid, and the color that you see is the potential contours for a given grid configuration. So it is a 2D code, but there is also a delta Z component, which is only used if there is something related to volume. And for all the related calculation, I have assumed delta Z to be 1 mm for all the calculation, but it can be changed in the main source code. And each grid cell has different kind of arrays which stores some properties. So there is a Boolean mask in the grid which stores if it is a solid material or if it is a vacuum. So if it is 1, it means it's a grid, and if it is 0, it means it's a vacuum. Then there are other properties like phi ij and nij for each grid coordinate, which stores its plasma potential and the ion number density. And dij and tij accumulates its damage on the grid and its temperature on the wall. And here in the code you can see that these are the type of arrays that I've defined for V rho is bound, which is for defining the vacuum and the material interface. Then the particle in cell routine, which is you simulate less number of particles, but each particle represents actual number of real particles. So you don't have to solve actual Coulomb equation to be more realistic. You can approximate it with less number of ions, but it is still very computationally expensive. So the way you do it is you inject a macro particle at the source, you weight it. So once the particles are there, it gets distributed under its own space charge and under the applied potential. And then you use some sort of interpolation scheme to know its weight and its nearest grid coordinate to apply the space charge on the grid. And then you solve the Poisson's equation for the potential and the electric field, and then you use the electric field using a particle pusher algorithm. Here in my code, I've used Boris pusher, which is the most up-to-date pusher algorithm, but there are like RK4, but Boris pushers is also recommended for the case in which you have magnetic field. For my current case, I don't have any magnetic field, but in case if there is, I think Boris Pusher does a very good job. Then if you have to do some collisions like Monte Carlo charge exchange or secondary electron emission events, you do that in some logic. And then you remove or delete particles. So the particles which hit the grids or particle which hit the end of the domain, you just remove them from the code. So to solve the electrostatic field, there is a 5-point stencil method. So you have this Poisson equation where you have the balance between your ions and electrons, and you numerically divide it into this stencil method, which is a very popular method for solving Poisson equation numerically. And then you have this sparse lower and upper matrix factorization method in which you split the matrix, which is very sparse. So a sparse matrix means most of the components in the matrix are zero and only the diagonal components dominate your matrix. And then you use different boundary condition. For this case, it would be a Dirichlet boundary condition on the material where you apply potential, and Newman boundary condition on the edges where you define the gradient of your electric field to gradient of the potential to be zero. And then there are Boltzmann equations. So for my current demonstration, I've used heavier electrons. So it means that the mass of electrons I have kept around 1000 mass of xenon divided by 1000, which is very heavy, which seems impractical at the point. But my goal is mainly to see the visualization of how electrons compensate the space charge. And of course, if you want to be very realistic, you can run it on a cluster. But for my PC, which is not very high end, I just made it heavier so that the simulation runs faster, but still preserve the space charge physics to see it in less time. And yeah, here is the electron density expression, which defines the electron density. And here is the minimum function, which defines here I've defined the minimum of phi and phi plasma to restrict the electron density from exploding. Because if this difference is even, let's say 20, this entire N0 term would explode and it goes out of bound. Just to limit that expression, I just made it so that it keeps it within the bounds. Then there is charge deposition and macro weight. So each particle represents a charge and of W real ions. And this is how it is interpolated. So you find the nearest cell, and the nearest cell gets the highest charge, and that's how you distribute. And by default, there are 40 particles per cell in my code, but it can be again adjusted if you go to the source code and readjust the density. So I think I need to go a bit quickly because I need to show you some demonstrations. I would skip some of the steps which are not that important. Then you solve the electric field on the mesh using this two-way interpolation, two-way finite difference method in X and Y direction. And once you know the electric field, you apply this Boris Pusher 2D leapfrog algorithm, in which you apply half kick and the rotation vectors just to push the particles. And this conserves your particles' motion and energy during the entire peak process. For ion injection, you use Bohm criteria because Bohm criteria is the criteria which defines the extraction of the ions from the two-grid optics. And the Bohm velocity is defined by this expression, where Z is the atomic number of the ion, and then T is the electron temperature. So electron temperature and mass of the ion. And 0.61 is your pre-sheet factor, which is defined by the drop of the plasma potential from the sheet to the extraction region by TE by 2 factor. So that's how the 0.61 factors come. And this is defining your ion injection current. And the velocity distribution is again randomly sampled. So you have in x direction your Bohm velocity plus some thermal randomness from this velocity distribution, and in y direction you have again a 0 to 1 random number generator, and then you generate a thermal velocity using this formula in y direction and in x direction. So now I come to slowly the demonstration part of it. So once you open the code, you would see different kind of parameter. On the right side, you see the window which defines different parameters which you can use to study the ion optics. So here are the number of grades, which is defined by n 0 to n. Voltage per grid, there is an option if you want to do the RF modulation as well. For each grid, it would apply a sinusoidal pulse as well. You can apply the intergrid gap and the chamfer angle and the material. And you can also have your custom material properties as well. There is an RF co-extraction possible, but the thing is, for my code, I have a heavier end. So for realistic simulation, you need to resolve your mesh size to the lowest dimensions. So if you have plasma frequency, you should define the mesh size based on that. But for demonstration purposes, I have made the mesh size to be of micron and the electrons to be a bit heavier. And this is the expression which is used to apply the RF sinusoidal pulse. And this can be used for co-extraction. There have been like some ion sources. The most famous one that I can recall of is the iodine ion source by a company called Trust Me, which demonstrated the iodine propulsion in space. And those collaborators have demonstrated RF co-extraction with electrons and ions as well. But I believe that RF co-extraction is still not very efficient. It is still possible, but it's not still very efficient because it causes a lot of sputtering and a lot of instabilities in your plasma flow. And then there are Monte Carlo collision, which you can, of course, do in the code. So this is the probability of collision for a collision to happen, in which you have the neutral gas density, your collision cross section, your velocity between ion target and the neutral ion and the neutral target, and delta t is the time step of that event. And there are some features which I've introduced recently in which you can use the empirical fit, which is only for xenon. So currently the code is xenon plus some other gases, but you can also use imported table. But I found few bugs in the user imported table, which I still need to fix. Then for charge exchange collision, for xenon, I've just used this empirical formula for a charge exchange collision to happen. So you have the velocity, which is g, and then you have this empirical fit from this Pullen's paper between xenon ions and xenon gas. And the way the plume expands from the screen grid aperture is defined by this analytical expression. So where R is the radial location and RT is the radial extent of your domain. And N0 is again your neutral density. And I took these from Lubos Breda's very nice article called in his website called Particle in Cell Consulting, where you can find a very good explanation of how to use this expression to model the expansion of the neutrals. And secondary electron emission, so when ions hit the grid, they impact, they release secondary electrons. And for this, there is a very simple formula for the secondary electron emission. Again, if so, it clips the value between 0 and 1, and whatever the energy of the secondary electron, if it exceeds 0 and 1, it would again, the clip function would keep it between 0 and 1. That's the formula. And E is the energy of the electron. Sputter yield. So after secondary electron, there is again sputtering, which happens with the incident ion. Again, it is a very simple analytical formula, but again, you can use any detailed formula, which I still need to improve because there is an effect of angular sputter. So I have still not included the angular sputter yield as well. And this sputter yield again accumulates over time to the damage that occurs on the grid. So once you have more sputtering, you would see more damage happening on the grid. And then there is this factor called K acceleration, which is accelerating your simulation by a factor of millions to see the sputtering at a faster rate. So this is defined by this ratio, which T real by T simulation. So let's say if you have a 1,000-hour test and your simulation is only for let's say 20 milliseconds. So if you want to compare both, you just take the ratio and it gives you an approximate acceleration factor, which you can again change during the while running your code. So these till now it was all related to acceleration, and there are other things which I can show you during my demonstration of the code. And then there is this another code which is called IBSIMU-GUI. And this is based on IBSIMU, which is a very well-known code for ion optics design. But what I've done is I've made this very nice graphical user interface in which you can do the same thing as you have done in PY-BEMCS, but it gives you the same kind of results. But since IBSIMU is already very well benchmarked with other code, I believe this is a very good tool to be used again. And here you can see there is a option to run this perviance scan, in which you can run the perviance scan, which would give you the emittance plot, the beam trajectories, and the divergence versus perviance curve, and also the intercepted current on the accelerator grid for different parameters. And yeah, this also supports 10 up to 10 electrodes with individual gaps, aperture radius, and it has different types of beam selectors with custom charge to mass options. And then there are some auto optimizers which you can use to find, let's say if you want to find a minimum beam divergence for a particular electrode configuration, you can just put this electrode range, and it would overrun, it would rerun the simulation multiple times, and it would give you the minimum beam divergence electrode configuration. And then there is also an auto optimizer which would run a multi-parameter grid scan, which would vary the gap, vary the grid voltage, and vary the aperture radius to give you the minimum beam divergence. I think that's all for now, but I would quickly now move on to show you how to deal with the code. So I guess you can see the screen, right?
Yes.
Okay, great. So to download this code, what I would do is there is this repo which I've created on GitHub. So anybody can just go, and if you're good with command prompt, you can just use git clone command, or you can directly download the zip file, and it would download a zip in your computer, and then you can unzip, and what it would do is it would extract all these files in the code. So in this code, there are two main files. One is the main.py, and the other is the physicsengine.py. So the main.py is mainly used for the GUI, which you see on this on the screen, and sorry, this one. And the physics engine.py contains all the physics which I explained during the presentation, all the interpolation scheme, all the particle push algorithm, all the finite difference method, and all the material properties. So to run, what I would do is I would come to, so let me go back. So this is my home directory. And here I'll install here this in PY-BEMCS. So I would cd into PY-BEMCS, and there is one more. So I will go again. And in this, if you see, there are all these folders. And what you can do is there is a folder called Python. So you need to go inside Python and go cd Python. Sorry, it's capital P. And if you do ls, and here you have all your important files which are needed to run. and it runs both on Windows and Linux, but I prefer Linux over Windows. There are some dependency that you might need to install, which I've listed in this README file. And if you go down, you can create a virtual environment, which I always prefer, so that I don't have to. And these are all the core dependencies which you need SciPy, you need Matplotlib, you need Qt5 for the window, and you need Tai for some GPU acceleration, which you might. So just do a pip install, and it would install all these files. So to run, what I would do is just Python main.py, and if I do this, it would open this GUI. But the thing is, I cannot run it because it's a pig code. I'm afraid that running over the call might freeze my PC. But I can still show you some features which I've already saved in the GUI. So this is your DC voltage. Um, so this is your grid one, where you can define your DC voltage, your thickness, your gap to your next grid. So gap between two grids, your hole radius, and your chamfer angle if you want to chamfer your grid. So it makes an angle. And here is your grid two. And if you want to add another grid, you can add. So let me to start the simulation, first you need to do is build the domain. So once you click build domain, it would run the solver, and then it would create this potential profile. Let's say if you want to add one more grid, I add one grid, and I put some arbitrary voltage with some random values. And if I do build domain again, it would take a while, but yeah, oh, there is an issue because I did not specify a gap. Maybe I need to do it. Oh, yeah, I think it's. And if I do it, and it would build a domain, and then you would have three grids separated by 1 mm each. So this is how you define the grids. Then in advanced parameters, you can define your neutralizer distance. So right now it's at the very end, like almost at the end of the domain, but you can make it anywhere in between the domain as well. You can define the neutralizer radius. It's just one-dimensional radius, so it's 3 mm. You can also change your plasma potential offset, which is used to define your boom velocity. You can change your electron mass ratio. So this is mass of xenon divided by some factor x. So you can make it as realistic as you can. And then here you can define your domain dimension as well. And just to run the simulation, you can just start the beam. There are other features. So if you want to export the particle properties like velocity as a function of time, you can just record kinematics and start the domain. And once you are satisfied, you just pause the beam and export the particle data as CSV. There is another function called show energy distribution. So here you can see the energy distribution of all the particles, ions, charge exchange ions, all electrons, or only secondary electrons. Again, these all can be customized in the main source file, which is also possible. And then if you want to record like a very nice GIF animation of this entire screen, what you can do is just click on this, record frames, and start the beam. And once the beam starts and once the beam stops, you can save the GIF animation anywhere you want. Here is another feature called ion beam species, where you have xenon and all the other ion, but here you can also change it to whatever you want. And then here is the material for the grids with different properties, just the most common materials which are used for ion optics. And here is a custom option where you can just change everything which you want. Again, this is possible. So just to show what the simulation looks like, so this is like a typical example in which you see charge exchange ion flowing through the gap and then getting deposited. And here on this temperature, you can see the thermal effect of the grid. Of course, the thermal effect is also very much accelerated, which you can again control using the acceleration factor in the source code. And here is the damage map, and here is the settle point potential, which is the potential exactly at the center of the acceleration grid. And then this is the case in which you have RF modulated co-extraction. So here you have electrons and ions both getting extracted. And here you can see the potential at the center of the saddle point varying as a function of time. And here is the beam divergence. I don't know why my internet is so slow, but you can go to this GitHub repo and check it yourself. And at last, you have the electron beam neutralization. So here in this case, I've just increased the rate of electrons, and you can see that the electron beam divergence narrows down if you have more electrons in the beam. So these are all the things related to this. And quickly, so I'm not running in this. I have also included this another feature very recently last week, which is called the Excel grade erosion profile, which measures the erosion profile, 1D erosion profile depth as a function of time, which you can see if you install it. And now quickly, I would like to also show you the other code, which is called IBSIMU-GUI. So if I go back and I open this, again, for this, you just need to go to this other repo, which is this. Again, you need to install IBSIMU as well. And all the instructions are given in this thing. And it's just one sudo command, and then you would be able to do it. It's much easier to do it in Windows and a bit trickier to do it in much easier to do it in Linux, but a bit trickier to do in Windows. So if I run this beam-GUI.py, it would open this GUI, which would run the thing. And then here you have all the other parameters, which do very similar things as the previous code. But again, the engine is here I can run it quickly because it is not a big code, so it's more of a trajectory code, so it should run quickly. So here you can see the emittance plot, and then this is the 3 sigma ellipse, which is used to calculate the beam divergence. And here is your beam profile, the radial profile exactly at the exit of the grid. Here you see the beam envelope as a function of x direction. So here x means the z direction in 3D. Here you have the electric field, here are the convergence plots, and here is the energy distribution because it's 8 kV, so everything is 8 kV. The perviance scan, which I wanted to show, is this one. So here you have two ways to do perviance scan, the voltage and the current scan. So let's say I want to do a voltage scan between 2 kV and 15 kV in steps of 8, and at the source density, at the current density of 600, let's say 100 ampere per meter square, which is very low. And I want to measure their divergence at exactly at this point of the acceleration grid. And there are different method of measuring divergence. Like you can make the sigma 1 ellipse, the ellipse 1 sigma, 2 sigma, 2.5, depending on how much area you want to cover. And then there are different direct RMS, FWHM method. I've included all of them, whichever you prefer. So if I run the scan, what it would do is it would start doing simulations and trying to measure the beam divergence as a function of each current, each voltage. And yeah, and it is a bit different from the previous code because here in this IBSIMU, you assume plasma to be at 0, and with respect to plasma, you define the potential on the grid. That's why you have grids at negative voltages. So yeah, it is a typical curve, but probably because the current value and the density value are a bit odd, so you don't get this typical U curve. But once you have this U curve, you will get a curve something running like, not in this. I think it was in my presentation. Something like this, like a U curve, which is a proper perviance divergence characteristics. So yeah, I think that's all from my side. If you have any question, I'm already ready to answer.
Well, thank you very much, Burak. I really appreciate your time on this. I would ask many questions
Yes.
for the physics engine, but we don't have time for that. But maybe How about this? I think you're using artificial mass ratio, right? You're
Yes.
making your electrons heavier,
Yes.
so in a way, it's an artificial mass ratio. But how does
Yeah.
this change the physics, collision physics? Like, does your engine have an ionization collision
Yeah, I mean,
operator on?
it would change a lot of physics. I have
Yeah.
not
So
tested it with the real electron mass because my computer, I don't have access to a HPC, so it is one of the tests which I need to benchmark, and how
yeah,
the mass ratio scales or changes the physics. I've only tested it to see if it does realistic physics, like it does the space charge compensation, which it does. It makes your
yeah,
perviance characteristics, which it does, but I've not compared it to how different it is from a realistic electron mass, which I would need to do to benchmark it, like on a real HPC machine first, and then come up with some sort of scaling or interpolation scheme that if you have certain mass ratio, you can
yeah.
approximate
Okay.
it. Yeah.
Yeah, I think the internet connection seems to be very weak, but I can still hear you. So I will just
Yeah.
continue with my next question.
Yeah.
All right. So yes, artificial mass ratio, it affects the collision physics. So I am doing a Hall effect thruster simulation, okay, full of kinetic code. Perhaps you've seen on my LinkedIn, and we use
Yeah.
also
Yeah. Yeah.
artificial mass ratio, and we have to modify the collision cross sections, right?
Yes.
And so perhaps you might need something similar.
Uh-huh.
So I'm just going to ask the classroom if any questions to Barak. It doesn't have to be simulation or ion trusses. It can be more general, carrier-wise. So think
Yeah.
about it. In the meantime, I will ask another question. So,
Yes.
so um, you actually build an ion thruster, right? I can see in
Yes.
your schematic during your
Yes.
PhD, right? You
Yeah.
actually built a physical thruster. And
Yes.
how did you validate your simulation curve,
Yes.
IV curve, with your actual thruster IV
Yes.
curve? How,
I
okay.
think let me if I can find the I have this in one of my papers which I don't have the access right now, but we validated the
No,
perviance
that's fine.
diver
That's fine. Yeah,
we did validate the
that's
perviance
fine. Yeah.
characteristic with the experimental data. Yeah.
So it looks good. I mean, if you look into
Yeah, yeah.
perviance,
I mean,
you can see
the only difference was the value of divergence which we measured experimentally was higher than the simulation.
yeah.
One of the reason was because the simulation was single aperture and the experiment was multi-aperture, so that caused some space
I
charge
see.
issues
Yeah, yeah.
as well.
Of course.
And the other reason can be what was the other? I think one of the main reasons for this, but the optimal perviance value for both the curves was the same. So they arrived at the optimum perviance at the
Yeah.
same
All
point.
right.
Only the difference was the experimentally measured divergence was bit higher. Another reason might be the resolution of our Faraday cup array. So if I had more number of Faraday cup array, maybe we could have resolved the divergence much finer.
Okay. Yeah. Okay. Nice. Nice. Maybe we can see. We can check one of the students. If anyone is interested in ion thruster, hopefully they can
Yeah,
go read your paper.
yeah, yeah, yeah.
All right. All right. Okay. Any questions, guys, girls, everyone? I will go with the next one then.
Okay.
So I see you using a tungsten cathode, right? The tungsten cathode for the ion chamber in your thruster. Use a tungsten, not a
Yes,
hollow
yes.
cathode.
No, no, no. It was not a
So
hologram.
what was your lifetime of it? Yeah.
Well, our the
Because
the
yeah,
the original
they're very
motivation,
fragile. So
yeah, it is very fragile. So the original
yeah,
motivation for the
yeah,
because the group that I joined during my PhD was neutral beam group, which is used for neutral beam ion sources, and all these ion sources are filament based ion sources. So
yeah,
they what they wanted to do is convert their existing ion source design into like for space application. And at that time, they did not have access to these hollow cathode ion sources, so they wanted
Of
me to
course,
just
yeah, of
focus on
course,
filament based.
of course.
But as far as I know, the only time I changed my filament cathode only twice in the period of 5 years of my PhD.
Oh,
So every
okay.
time I opened, I mean, you have to be very, very careful not to while cleaning your eyes. So even if you touch it
Wow.
accidentally, it just breaks, and
Yeah,
it once break because of that accident. Otherwise, it lasted really long. And the other reason was because my iron source was not a very continuous iron source because we use stainless steel grids, and the problem with stainless, it was bending a lot, causing a lot of arcs. So we used it in
yeah.
pulsed operation. So instead of continuous operation, we move. So that's one of the reasons why the lifetime of our cathode was a bit larger, let's say 5 years, because we did not operate it very long hours.
I see. All right. I can go a lot into detail, but I want to go change the topic. Maybe
Okay.
career-wise. If you just
Yeah.
started your PhD just now, what would you do differently? Or
Uh,
would you still do, yeah,
well, if I would start my PhD just now, I would, let's say in the current moment, I would think because AI and machine learning and all these algorithms are way faster. So uh,
yeah,
5 years before, I used to struggle because I did not have a computing background or scientific computing. So for me, it was very difficult to learn programming, but I learned it eventually, but it took a lot of time.
yeah,
And nowadays, you don't even have to spend a lot of time because
yeah,
AI can do it for you.
yeah,
If you have Claude, if you have Gemini, so all what you need to focus is more on physics side, and you need to always cross check if it is doing the right things. So I think
yeah.
it saves a lot of time. Of course, it makes you a bit lazy, but you need to find a balance. So you need to understand the code as well, what it does. So you should not be blank. Whatever AI spits out to you, you should not believe it blindly. But I would try to use a bit of AI to accelerate my work, I would say, which
I think
I
it's a very,
struggle.
very good,
Yeah,
yeah. I think you touch on a very great point, and most of the students are not aware of that.
yeah,
They have
because
access to a great power.
Because I remember while writing codes for my beam profile measurement in MATLAB, I used to, at that time there was no ChatGPT, so
Yeah,
I used to, if there was an issue, I used to post my message in a forum, and I would expect that somebody would reply after 3, 4 days or 1 week or 2 weeks, and then I would
yeah,
correct it.
yeah,
And
yeah.
it was a very long and time-consuming process. But now you just put the code in ChatGPT and it gives you the perfect code, and it saves you so much time.
Uh, Exactly. I think this is a great. I wish I had too when I started my
Yeah.
PhD. I think I could do much better work now because I was working on with one of my senior researchers' codes. I was using his
Yeah,
Fortran code, and it was
yeah,
like 5, 10,000 lines of codes, and
yeah,
it's difficult to understand. But if I had access to ChatGPT, I think it would be much easier.
exactly.
Um, all right, and maybe career-wise, okay. Anyone questions, guys? Okay, one question. What's it?
Yeah.
Bir daha söyle. So the question is, how do you resolve the pits and groove erosion on the grids? How you resolve that? Or
So in pits and groove erosion, what happens is when an ion hits
so, yeah,
the grid, so there is a particular, depending on the material
yes,
property which you define, there is a particular threshold that if the energy of the ion exceeds that threshold energy, it would remove that cell, and then it would recalculate the Poisson
yeah,
equation, causing that to damage. And you can accelerate this factor. So you can make it like if it hits 10 times, it would erode one ion, or if it hit one time, it would erode. So you can change this ratio using this acceleration factor, which is like an arbitrary term.
yeah. I know you mentioned it. I mean, erosion is usually a function of both energy and angle, and I know
Yes,
you
exactly.
mentioned you will
So
include
I
you will
need to
include
include
it
the
in the,
angular
yeah.
dependence of the erosion as well. Yeah.
So maybe one question: are you able to update the geometry of the grid? Okay, you take the calculation and you know how much depth
Yeah, yeah,
is
yeah.
eroded, but do you
It's
update the
continuously.
geometry after that?
Exactly. It is constantly being updated as it is getting eroded. It would update and it would recalculate the Poisson
Okay,
equation at that same moment. So if you run the simulation for a long time, you would see the erosion happening in the grid. You would see the deformation of the grid as well. I've also included like the bending of the grids, like the thermal effect as well. But
yeah.
yeah, it's getting more and more complicated as you include more and more physics. So
Yeah. Yeah, I agree. I agree. I mean, all right. Hope that answers your question. Anyone else? All right. I think one more last question because
okay.
I don't want to take too much of your time. So, what do you want to do next with this open source code? Hopefully, if one of my students are interested, maybe they
Yeah,
can continue to contribute
yeah,
this. But what
no,
do you want to do
no.
yourself
I just
personally?
want personally, it's one of my personal project, and it's for me, it's like if it helps solving someone else's problem, it's more than useful for me. I
Yeah,
don't want to make it commercial. I don't want people to use it for commercial purpose. But if it
yeah,
is being used for academic or student research purpose, I mean, I'm
yeah,
more than willing to help or do it like because it's
yeah,
my. I have my personal affection towards this because I started it. So I would be more than happy if it is helpful for somebody else's thesis or if it is included somewhere. So I would
great.
be
Yeah,
more than happy to contribute more. I mean, I'm still doing contribution daily or at least at once a week to add something new to the code or fix some bugs in the code. But yeah,
yeah,
all
great.
the suggestions and contribution are more than welcome. I would be happy to help or suggest anything.
All right, that's great to hear. You
Yeah,
can support. Thank you for doing this,
no
really,
worries, no
because
worries.
I know how time consuming and to
Yeah,
debugging a code, writing a code, and you're putting a lot of time into that. I can feel your pain. So thank you
yeah,
for doing this. So not just
no
for us,
worries.
obviously,
Yeah,
for the
I mean, you can
community.
use both the course, the one IBSIMU-GUI, which is
Yeah,
already, so you don't even need to benchmark that because it's already a well-known code. But if you want to add some features in the GUI, so it can be used for some other thing, that can be done. And the other, the PY-BEMCS, which we still need to benchmark with a lot of things, but it's still a
yeah.
development phase of that code. So.
All right, all right. That's great.